Welcome back everyone. Today we are going to continue on with our applications of differential calculus by considering rates of change. So we know that the derivative represents the gradient. So when we're finding the derivative, we're finding dy dx. And another way of writing this sometimes is the change in y over the change in x. And when we're talking about this, change in y is sometimes known as rise, and change in x is sometimes known as run. So when we say that the gradient represents the derivative, that's in relation to a curve. So if we've been given a function, an equation, a curve of some kind, then when we find the gradient, dy dx, we're measuring the rate of change of y with respect to x. But the derivative can actually measure rate of change of a whole lot of other variables as well, not just to do with gradient and not just to do with functions that we sketch. So it's a measure of the rate of change of one variable with respect to another. If you imagine blowing a balloon up with air, it will start small and it will gradually get bigger. So we can talk about how the volume changes with respect to time. So that would be dv dt, the change in volume with respect to the change in time. Also, the volume will change with respect to radius. As the radius increases, the volume will increase as well. So that one we could write as dv dr. So the rate in change of volume with respect to the radius. Or we could have how the radius changes with respect to time. So over time, rate of change of radius with respect to time. And this is happening because as the balloon gets bigger, the radius will be increasing over time. When we talk about the average rate of change, we're finding the gradient between 2 points. So when we talk about the average rate of change, if I had a particular function, we're wanting to find the gradient between 2 points, and that's going to describe the average rate of change of the function. We do that by using our formula for gradient between 2 points, which we've often seen written as follows. When we talk about average rate of change, we often write it slightly differently, but it means the same thing, average rate of change, some abbreviations there. We have f of x2, so as in we sub in our second x value to get our second y value, minus f of x1. So we sub in our values there, over x2 minus x1. It's essentially, though, just the formula for the gradient between 2 points, average rate of change. Here's a past exam question that asked about average rate of change. So we've got a function there and we wanted to know the average rate of change with respect to x on the interval 1 to 3. So I need to find, I've got here my x1 value is 1 and my x2 value is 3. So to find f of x1, that means I'm substituting 1 where the x is, so I'll get 1 cubed minus 4 times 1. 1 minus 4 gives me negative 3. And then f of x2, so we sub in 3. We've got 3 cubed minus 4 times 3, so that will give us 27 minus 12, which would give us 15. So we want to now use that average rate of change formula we just learnt about. So to find the average rate of change, we've got f of x2 minus f of x1, be careful with your signs there, over 3 minus 1, 18 over 2, which will give us an average rate of change of 9. The other type of rate of change we learn about is called the instantaneous rate of change. So if I'm talking about the instantaneous rate of change, instead of wanting to know the rate of change between 2 points, as we did before, we want to know the rate of change at one particular point. We can either do this by drawing a tangent and finding the gradient of this tangent, or the better way is to find the derivative, the value of the derivative at this point. So not just the derivative in terms of x, but we sub in the point to find the value at that point. Let's have a look at a couple of examples. In this example here, we've got that the volume of water in a reservoir is given by this particular function. We want to find the volume at a particular time, and then we want to find the rate of change at a particular time. When I'm wanting to find the rate of change at a particular time, that means, even if it's not quite written, that we're finding the instantaneous rate of change, okay? Which means we do it by finding the derivative at that point. Let's look at question A first. We want to find the volume in the reservoir at time t equals 10. This means that I'm subbing 10 into my equation. Now this, when we substitute in, this is not one of our exact angle values. All of our exact angle values include pi, so we're going to instead put this into our calculator. Now in the exam or SACS, they will clearly tell you how many decimal places we want, or if you want to round to the nearest litre or anything like that. Unfortunately, let me just move this over here. Unfortunately, our textbook and some of the examples often don't do that. We make sure that we're in radians whenever we're dealing with trig functions, and we can type in our equation here. We want sine of, I'm just going to use x instead of t because it's a bit easier, but you can use t from the variable menu if you wish. But sorry, no, we're not putting in x, are we? We're substituting in 10 at this point. Now, obviously it can't simplify. We're going to do this correct to 2 decimal places. We can tap up here to change to a decimal. So we're getting 4.196. If we round this correct to 2 decimal places, that would be 4.2. So our volume at this stage is 4.2 litres. So we've got 4.2 litres in the reservoir at that time. Part B now, we want to find the instantaneous rate of change, which means I need to find the value of the derivative at that point. Because I was given v of t, the way I would write the derivative is v dash t. We haven't yet learned how to differentiate sine, so we're going to use our calculator instead. We will get to differentiating sine later on, but for now, let's use our calculator. So I'm going to take my function we had here. We want to, x is our formula there. We must be in radians whenever we're dealing with sine, cos and tan functions. Interactive calculation diff. I'm going to diff with respect to x. We get this value here. Now I actually want to find the rate of change at time t equals 10. So I can now choose to substitute in when I've used x instead of t, remember. X equals 10. And if I want to give this as a decimal, we've got our decimal negative 0.4. So that means that the rate of change, it means that the water in the reservoir is decreasing because my rate is negative. So it's decreasing at a rate of 0.4 litres per minute. One other way we can do this in our calculator, which is quite useful, if I was to copy my value down here and try again, another option is this one here, derivative at value. So this means I'm going to straight away say I want to find the value of this derivative at 10. And it goes straight to that answer we had before. So that's a useful thing to use as well. So let's pop back in here. Oops, sorry everybody. Let's close that. Okay, let's pop back in here. We've got our derivative here, v dash t. So we know that we worked out that it had on our calculator was equal to half cos of t over 4. And when we substituted in v dash 10, we ended up with negative 0.4. In order to determine the units, the other way that we could think about this is we've differentiated volume with respect to time. So that means our units are our units of volume divided by our units of time. So we have our units of volume divided by our units of time, which was hours. So if I'm describing this, if I had to just describe this rate of change, I could say that what's happening is that the volume is decreasing at a rate of 0.4 litres per hour when t equals 10. So it's not always decreasing. Remember, our sine graph generally is periodic, so that means the volume of water is regularly increasing and decreasing. So at other times, it's going to be increasing. But this is what it is at time when t equals 10. The other application we can look at when we're talking about rates of change is motion in a straight line. Motion in a straight line is also known as kinematics, which those of you who do physics or specialist maths might have heard of. Position is given by the function x of t. So that means position is where we're located. We consider 0 the origin, values that are positive are to the right, negative values to the left, and position is where on this line a particle is located at a particular point in time. Velocity is related to speed, but the sign tells us the direction that we're moving in. So if the sign is positive, it means the particle is moving to the right. If the sign is negative, it means the particle is moving to the left. And if the velocity is 0, it means that the particle is not moving, which also happens when the particle turns around. To get velocity, we differentiate position. So we can either write it as x dash t, derivative of position, or as dx dt, derivative of position. Acceleration is to do with if our particle is speeding up or slowing down. And the sign helps us to determine that. To get acceleration, we differentiate velocity. So we can write acceleration as a of t, or v dash t, because we differentiate velocity, or we could write it as x with 2 dashes, t, x double dash t. When we've got 2 dashes here, it implies that it's the second derivative. That just means that I've differentiated twice. So if I start with position, I differentiate once to get to velocity, I differentiate a second time to get to acceleration. We can also write it in our other format, so acceleration is the derivative of velocity, or it's the second derivative of position. We differentiate twice. Let's see an example together. Okay, a particle moves in a straight line so that its distance x centimetres from a point at time t seconds is given by this function here. We want to first of all determine the particle's initial position. So initial means where it is at the start, so that's when t equals 0. If I was to substitute 0 in, I will get 0 minus 0 plus 0 minus 2. So that means that my particle starts to the left 2 meters. I then want to find the velocity and acceleration after 2 seconds. So to find the velocity, I differentiate. So I multiply by the power, I subtract 1 from the power, I multiply by the power, I subtract 1 from the power, I multiply by the power. My acceleration formula, I differentiate again, multiply by the power, subtract 1 from the power, multiply by the power. Remember, derivatives of constants is 0. So to find the velocity and acceleration after 2 seconds, I'm going to substitute in v of 2. So that means it'll be 3 times 2 squared is 4, minus 4 times 2 plus 1. So that's going to be 12 minus 8 plus 1. So the velocity is 5 meters per second. It's positive, so it means after 2 seconds my particle's moving to the right. If I want to find the acceleration after 2 seconds, I substitute in 2. So I've got 6 times 2 minus 4. So 12 minus 4, that's 8 meters per second. 8 meters per second squared is how we give velocity. Let's come back here, get my pen back. 8 meters per second squared. Next, for part C, we want to determine when and where the particle has 0 velocity. So that means I need to let my velocity equation equal 0. We can factorize this. Our only factors of 3t squared are going to be 3t and t. My only factors of 1 are 1 and 1. And I'm going to need it to be negative there. And let's check. This will give me negative 3t minus t, which gives me negative 4. So this means the velocity is equal to 0 when t equals 1/3 and when t equals 1. That's the when, but we also need the where. So for the where, we need to substitute this in to my position equation. So where relates to position. So I'm going to have x of 1. Let's work out that one first. So I've got 1 cubed minus 2 times 1 squared plus 1 minus 2. So that's 1 minus 2 plus 1 minus 2. That's negative 2 meters. X of 1/3 is a bit trickier. 1/3 cubed, that's 1 over 3 times 3 times 3, so that's 1 over 27, minus 2 over 1 squared is 9, plus 1 over 3 minus 2. Let's work out this on our calculator, shall we? You could do it by hand, because remember, exam 1, they are going to test your fraction skills. But for today, let's just pop it in here. So we've got 2 over 9 plus 1 over 3 minus 2 gives us negative 50 over 27. Okay, so we've got an answer here of negative 50 over 27. If we wanted to, now can we change this? Yes, we can. Okay, let's highlight this and say interactive transformation fraction to proper fraction. So it's the same as negative 1 and 23 over 27, which is not a fun number, but one that we're going to need to use for what we're doing here. So negative 1 and 23 over 27 is how it is as a mixed number. So let's go back in and write this down as our answer. So we've got here negative 1 and 23 over 27. Finally, for part D, we want to find the total distance travelled by the particle. It starts at negative 2, okay? After, remember, whenever the velocity is equal to 0, when we have 0 velocity, this means that it stops, and often that it changes direction. So we never have a change of direction unless the velocity is equal to 0. So we've started here at negative 2, then after 1/3 of a second, it's travelled slightly this way and got to -1 and 23 over 27. The distance it's travelled, the distance between these 2 points here, is only going to be 4 over 27, okay? To get up to a total of 27 over 27, we've got a distance of 4 over 27. After 1 second, it's back at -2, so it then goes back this same distance to get back to -2. So we've travelled another distance of 4 over 27. So the total distance travelled by this particle oh, we should have said something here, shouldn't we? Let's say find the total distance travelled by the particle in the first second, because obviously it could keep travelling. But within the first second, by the time we get up to x equals 1, is going to be 8 over 27 metres. If we wanted to know how far it travelled by the time we got to the second, then we'd have to see where is it after the second by substituting in t equals 2. Presumably it will be further to the left, because our particle, it travelled to the right briefly and now it's going to continue on to the left. It only changes direction at those, it changes directions here as well, so it'll be heading back that way presumably. So this is kinematics. This is an example of what's going on here. Once again, if you have any questions, please feel free to let me know in the comments or via emails. And if you spot any errors, please let me know as well. Thank you for watching.